In this video, we're going to begin to speak about the model that was used in the expert elicitation. We realized that no matter what method we use to estimate this probability of establishment, we were going to require experts to fill in the data gaps that existed, because there is no data on the probability of arrival or passage or colonization or spread. So the team began to identify experts. In the meantime, the team also began to identify models that would be used. Excuse me. Over the next couple of months, we investigated many ideas. This was one of the earlier files that we used to try to think this problem through. And the details are not important. All I would like you to understand is that we were using many different ideas. And somewhere along the line, we came up with the idea of counting fish. That fish counting was going to likely be an essential part of whatever model we finally came up with. So here is the model that we eventually used, and here's the basic rationale. Or logic, perhaps I should say. But first, let's get oriented to the model. In column B, we have years from 2015 through 2071. 2071 marks the end of the planning horizon. In column C, we have the number of fish that might pass through the system annually, given that there is a small population present in the area between the Dresden Pool and Brandon Road Lock and Dam. So we are essentially saying that downstream of Brandon Road Lock and Dam, there could be a small population of fish. There could be a medium population of fish, and that provides a greater propagule pressure. There could be a large population of fish. For now, pay no attention to the size of the numbers of fish. This is a test model that was just trying to work out the basic logic. But here is the basic logic, that over time, randomly, different numbers of fish could pass through the system in a year. So if we come over here to column H, we could add up the number of fish that pass through the system, given that there is a small population pushing the fish through. So by 2021, that would be years 2015 through 2021, we could have 420 fish get through. 2021 is chosen because that is the year that would be the earliest time by which a non-structural plan could be in place, or that the lock could be permanently closed. We also counted the number of fish through year 2031. 2031 was chosen because it is the earliest year by which some of the more complex technological alternatives could be implemented. So in this case, we had 794 fish that could have passed through by 2031. And by 2071, we could have had 3,506 fish pass through. Now, what we need to know is, if you had numbers of fish like this, would that be a problem? And that led us to the idea of a colonization threshold. Again, I will say, don't worry about the numbers here. These would be numbers that would eventually have to be provided by experts. But for right now, these are just dummy numbers that are used to get the model logic worked out. So we said, suppose you had to have 4,695 fish pass through between now and 2021 in order for there to be establishment. Now that would be regardless of the size of the population that's pushing. So what we would do is we would compare the small population, 420, to 4,695, and we would say there would not be colonization. Then we would look at the median population, 2164 compared to the threshold. We'd say no, there would not be colonization. But if we got 12,198, that is larger than 4,695, and we would have colonization. A similar check was done for the year 2031, and you can see that here. A similar check was done for the year 2071, and you can see the results here. Now, what we need to know is which of these values do we choose? For 2021, there are 3 values. So up here we have a population size that arrives. Here by 2021, you can see number 1, that's a small population. So that says go down here, look at 2021 and the small population, take this number and put it right there. For 2031, also small. So we look at 2031, 2031 and a small population, take this number and put it here. In 2071, there was also a small population, so take this number and put it here. Now, if we calculate this a great many times, and here's where we introduce randomness to the model, that we know this is not the number of fish that would be entering in a year, and we know that we don't know what the colonization threshold is, nor do we know what size population will arrive, so we're going to randomize all of that. And let's begin here by looking at the pattern of fish. It could be this, it could be that, it could be any of these things. And you'll notice that as these patterns of fish arrival change, so do the total number of fish, so do the thresholds, and so do the patterns of colonization. So up here, for example, we have small probability, a small population of fish arriving by 21, a small population by 31, but by 71, there would be a large population of fish. So what I would like you to notice is these numbers change here. Colonization, 0s and 1s. And if we calculate this many times, like 10,000 times, and find out what the average is, we obtain these numbers. This is the probability of colonization that is calculated from the model. The probability of colonization by 2071 is 36%. It's 12% by 2031 and 3% by 2021. We can use basic statistics. We have a proportion here. We have a sample size of 10,000, and that yields a probability distribution that is normal, that gives us a probability of colonization. So we have used fish counts and a colonization threshold to estimate the probability of colonization. So this model estimates the probability of colonization. We have a probability of spread. The probability of spread times the probability of colonization yields the probability of establishment. And this is the value that we're after. So we felt comfortable that we had a model that would get us to where we want to go. Now what we needed were the data to make this model go. So you see here is the model without any data, value errors everywhere because it lacks data, and these are the inputs that we would need from experts. So we needed to know what is the probability that a small population would arrive at Brandon Road by 2021, 2031, and 2071. We needed similar estimates of the probability of a large population by these three different time frames. Then we were going to ask our experts how many fish actually pass through the system. If there is a small population pushing fish up toward the Brandon Road Lock and Dam, how many fish would get through in a year? And how many fish would get through in a year if we have a medium population and a large population? And of course, all of this information has to be dependent on a particular kind of scenario. In this case, we're talking about the without condition or the existing condition. Without basically means without taking any additional steps to prevent the spread of aquatic nuisance species. After the expert provided this information, we would ask the expert the probability, or not the probability, excuse me, we would ask the experts the size of the colonization threshold. So for example, here we would say, imagine the number of fish that could get through the system between now and 2021. What would be the threshold of fish that would convince you that there could be colonization? Clearly that number is unknown, so we would ask the expert to estimate it, give us their minimum estimate, their maximum estimate, and then we give them 2 percentiles to break the curve. We'll explain these inputs a little bit later. For right now, let's just understand what the inputs are. And then we would ask the expert, given that there is colonization, what's the probability that they will spread? And once again, the values are estimated with 4 data points. Then we change the scenario to a non-structural plan. Once again, we ask about the population arrival probabilities, and we ask about the number of fish that would pass through the system. We then move to technology alternatives like the electric barrier, complex noise, the electric barrier and complex noise, and lock closure. For each of these scenarios, we simply ask the number of fish that would pass through the system under each scenario. Once the expert provides that information, we would have a completed input data sheet, something like this. These numbers power up the model and enable us to estimate the probability of establishment.